The figure shows a cartoon picture of a device known as a mass spectrometer. In this type of mass spectrometer, the atoms or molecules under investigation are first vaporized and then ionized by an ion source. The ionization process removes one electron from the particle, leaving it with a net positive charge of plus 1e. The positive ions are then accelerated through the potential difference v, which is applied between the ion source and the metal plate. With the speed v, the ions then pass through a hole in the plate and enter a region in the spectrometer with a constant magnetic field B, where they are deflected in semicircular paths. Only those ions following a path with the proper radius r strike the detector, which records the number of ions arriving per second. The mass m of the detected ions can be expressed in terms of r, b, and v by recalling that the radius of the path followed by a particle of charge plus 1e is given by equation 21.2. In addition, we can derive an expression for the speed of the particle after being accelerated by the potential difference. We do this by using conservation of energy. The change in electrostatic potential energy of the ion will be equal in magnitude to the change in its kinetic energy. Eliminating v from these two equations algebraically and solving for the mass gives the following. This result shows that the mass of each ion reaching the detector is proportional to b squared. Experimentally changing the value of b and keeping the term in the parentheses constant will allow ions of different masses to enter the detector. A plot of the detector output as a function of b squared then gives an indication of what masses are present and the abundance of each mass. The figure shows a record obtained by a mass spectrometer for naturally occurring neon gas. The results show that the element neon has 3 isotopes, whose atomic mass numbers are 20, 21, and 22. Recall that isotopes are atoms that have the same atomic number but different atomic masses, due to the presence of different numbers of neutrons in their nucleus. Notice that the isotopes have different abundances, with neon 20 being the most abundant. Physicists use mass spectrometers for determining the relative masses and abundances of isotopes, and chemists use these instruments to help identify unknown molecules produced in chemical reactions. Mass spectrometers are also used during surgery, where they give the anesthesiologist information on the gases, including the anesthetic in the patient's lungs.